So you may notice up here is sustainable and green, and I don't know if anyone is aware of the distinction, but green chemistry really has had a different kind of understanding than sustainable. And throughout the day, I'll explain this and try and draw out those distinctions a little bit more. But that title is for a reason. So I'd like to tell a little bit about what's in store for the day, talk a little bit about some of the historical drivers, and really talk about sustainability and living within limits. So my hope is that you understand about sustainability. You may have heard about that a little bit more. I don't know how much green chemistry has been tied into that in the past, but that's really one of the objectives we have for the day. I'm going to start and state my underlying assumptions because I think many times we are in situations where people don't tell you what their presuppositions, their assumptions are. And I think that we all come in with presuppositions and assumptions. We all have biases. The notion that scientists are objective is completely false, all right? Scientists are as subjective as everyone else. They're as subject to biases in thought and in experimentation like everyone else. And so it's really important that you understand that you too have all these biases that you bring forward. And we're going to talk a little bit about that and how that affects sustainable and green. And we'll talk a little bit about some definitions. Hopefully this will be a fun day, okay? We're going to try and maintain a lot of energy throughout the day. Hopefully you'll get to know one another by the end of the day. We've got an activity midday with some kids, which is really outreach and intended to be that way to get you used to speaking about green chemistry to people of all ages. Don't be afraid to ask questions. We'll try and deal with them in the moment. If we can't, we'll move on. Please be respectful about cell phones. I have a tendency to ask lots of questions. Sometimes you'll ask a question and I'll ask you a question back. It's not because I'm trying to be evasive, it's because I'm trying to get you to think and think in a different way. So please assume positive intent. If you do get sleepy, everyone's going to get sleepy, I guarantee it, especially after lunch. If you get sleepy, it's fine. Get up and move to the back room, stand for a while, go out, do whatever, put cold water on your face, do what you need to do, come back, okay? Doesn't bother me. Please do so. So one of the things that you have to understand about sustainability and green chemistry is it's multidisciplinary. The days of being able to sit in a laboratory or in an academic situation and just study one thing in a deep dive doesn't apply to green chemistry. Green chemistry and sustainable chemistry requires that you be a lateral thinker, that you think from a systems perspective, and it asks you to synthesize all of the information that you've learned to date. All right? You're going to be drawing on all aspects. So it's really important you understand that. If we have many NSF scholars, I know not all of you are NSF scholars in all probability, but many of you. And in reading those backgrounds, and I did read every single one, I was extremely impressed by the degree of diversity that was there. If you look around the room, you'll see there's a tremendous amount of diversity. That diversity is real strength. And the diversity in your backgrounds, in terms of scientific disciplines and understandings, and the diversity in the chemistry and the engineering backgrounds, the biological backgrounds, and medical, so on and so forth. All of those things are extremely important. We need all of that diversity in all of your minds to really solve problems. I have a tendency to be very practical because, again, I've come out of industry where we're all about application of these principles. I've spent an enormous amount of my career in trying to move big companies to become greener and more sustainable. So I'm going to try and impart some of the things that I've learned to you today. And it's really about how you think that we're interested in developing. We're going to move very rapidly. Each one of these principles, without exaggeration, could be a semester or more course by itself. Okay? And we're doing it in 20-minute clips. Okay? So understand that we're just brushing over these things very rapidly. You're just getting a very quick taste of things. And a lot of what I've learned has been in the batch chemical operations, okay, which is typical of pharmaceuticals, specialty chemicals, advanced materials, so on and so forth. I'm not as experienced in the petrochemical aspects. So a lot of what I will be talking about, and Rich for that matter, will be based on the batch chemical operations. So I don't know how many of you resonate with some of these words up here. This is what I grew up with in terms of DDT and mosquitoes particularly. It's still used in many parts of the developing world for mosquito control, but we all know that that bioconcentrates, and that was really the impetus for Rachel Carson to write Silent Spring. Chlorofluorocarbons, ozone hole, it's not a big deal, but again, the Montreal Protocol only came into being in the early 90s. And we eliminated those things. It's a great story because CFCs actually got rid of some problems, but they created another kind of problem. And one of the things that you'll understand is in sustainability is many times you will trade impacts. So it's either a greenhouse gas or it's a potent or a global warming type compound, or it's an ozone depleting chemical, or it's ozone creation potential. And people many times will optimize only one impact and forget about all the others. What I would like you to think about is optimizing multiple variables so that you reduce as many impacts as you possibly can. Cuyahoga River, this is a photo of that. It spontaneously caught on fire in the late 60s because there was so much petrochemical waste in there. And Love Canal was a community that the EPA bought and closed down. It was built on top of a waste dump which was made by Hooker Chemical Company. So again, I'm not sure if everyone is aware of these things, but environmental disasters are the root of green chemistry. Because green chemistry, as many of you probably know, was started by two individuals, predominantly actually three. The third isn't really spoken about too much, but Paul Nastis and John Warner and Joe Breen. And they were all at the US EPA in the Office of Pollution Toxics. John Warner was not. Paul Nastis and Joe Breen were. John Warner was actually at Polaroid. But they were the ones who were the primary impetus, and their interest was in elimination of toxics and waste. All right? So that's really what have been the historical strong drivers. Whoops, I want to go back. And what those drivers resulted in is an exponential increase in regulations. And that's all this is showing. So in the 1970s, early 1970s, we were here, and nowadays we're all the way up here. And as the US led, so happened in the rest of the world. All right, is a tremendous amount of regulations. So you are existing in a world which has a lot more regulations than what I grew up with when I was actually a lot younger than you and your age. The European Union takes a slightly different approach to regulations in recent years. And the one thing I wanted to bring out is this strong precautionary principle. Does anyone know what that is? Right. So the idea is that if you can't prove it's safe, you don't use it. This is a dividing line. In the United States, we don't use the precautionary principle, although there are many people who would like to rewrite TSCA to be more along those lines. But in California, the Department of Toxic Substances and Control, very interested in taking that kind of approach in their California regulations. So this is an extremely important principle that drives a lot of effort to try and eliminate hazard from chemicals. The other concept here is producer responsibility, and that is that a company is responsible for managing environmental issues as well as take back. So in Europe, for example, cell phones and that kind of thing have to be taken back by companies. In Japan, tremendous amount of work to reduce waste. If you go to Japan, one of the things that you'll notice right away is how efficient everything is. Electrical efficiency, water efficiency, everything else like that. It's an island culture, and they don't have large amounts of natural resources. So Japan is really driven very much by efficiency, and recycling is a big deal. Now China, as you know, is the most rapidly growing economy in the world. It's really overtaken the United States in many ways, and it will continue to do so. It's gone from a very dated sort of technology into the 21st century and beyond. An enormous amount of legislation. The big issue there is not all of it is enforced, but that's regulatory framework exists in China. And as you know, in Shanghai and Beijing and places like that, it's getting very hard to breathe. So the population is becoming very restive and experiencing kinds of things that the United States experienced in the 1960s and 70s. That is, the population's demanding that there be change. So this is where I'm talking about assumptions. And I'm sure that most of you came in the door with certain biases. And when I usually speak to people who are much older than you, I make the caveat that in all probability you're going to come in and listen to me and I won't change your mind, okay, because of these biases that exist. And many people's minds are made up about what are the big drivers in the world. I try and take a very broad-based view of sustainability. There's some big trends in the world that are driving things in the world in terms of politics, in terms of economics, and so on. So many people say, what is it that the Earth? Do we have a lot of resources available to us, and we can support not only 10 billion people of the world, but we can grow to 50 billion, and the Earth can still support it. Or you have those people who say, no, we're already living in the United States and in Europe and in other parts of the world at a rate where it would require 4 Earths if everyone in the world consumed resources. I come from the view that we have finite, limited resources, and they're diminishing. And I'm going to be making that case to you today. Do we have too many people, or we've got room for lots more people? And I come from the viewpoint that even at 9 billion, the Earth is tremendously stressed. We've got to do something about population. Most people don't like to talk about that. But if we don't get population under control, it's going to be very difficult for us to continue as a species. The environment will take care of itself. It's always adaptable, so on and so forth. We can stand to pollute. No, we can't. Not in my opinion. Again, I come from the point that we've got to stop doing this. We've got to be much more efficient in how we live. We've got to stop spreading toxic materials through the environment. The Earth is at a tipping point. It's stressed. And there are so many indicators of that that you're going to be dealing with in your lifetimes, much more so than what I've lived in. So there's a variety of issues and opportunities here, and I could make a list that's probably much longer than the one that you're seeing there. Each one of these things are driving the world in one way or another. And I could choose any one of these things, and I could talk the entire day on every one of them. But the point in the slide is to make sure that there are issues associated with these and tremendous opportunities. I'd like for you to think about the opportunities that exist. This is the problem that the world faces. We have tremendous vacuum of natural resources. We produce a few goods and services. A majority of what we produce spends less than 3 or 4 months in actual use before it's disposed of. The vast majority of the world's resources end up as waste. That's a fact. Another fact that I'd like to leave you with, I know this is an eye chart. It's worth having a look at another time in a quiet moment. There's the reference. But what this chart is showing is consumption of some few materials that are very valuable. And this is actually a better chart. As chemists, we like periodic table. What this is showing is that we've got some elements here that are going to go into rapid reductions very soon. Look at this time, 5 to 50 years. If I point out platinum group metals, and if I pointed to gold and silver, copper, indium, rhodium, a lot of those materials are things that chemists use on a regular basis. They're extremely important to them as materials. This is trying to show you supply restrictions versus supply risk. Look up here again, copper, indium, rhodium, platinum group metals. Again, do you think that these things are serious? They're very serious because your way of life depends on this. Indium is in every cell phone that you have, right? Every computer. It's in photovoltaics. We have less than a 4-year supply of this. Okay? Moreover, as is the case with most of these metals, indium is a product of secondary metals processing. So we have to mine tin, we have to mine zinc and lead to get indium. In the platinum group, we mine platinum, we get all these nice compounds that are among the rarest elements on the face of the earth. Iridium we only get from meteorites. There is a socioeconomic cost associated with these things. And I don't have a lot of time to go into this, but most of the platinum group metals come from South Africa. South Africa last year let go 50,000 miners because they were protesting for a living wage, and 34 of them were killed in a police action at one of the mines. That isn't even getting into the environmental mess that exists in South Africa. So for these materials that we're routinely using, they come at a high cost. I could talk about phosphorus. Phosphorus is in food. It's used in chemistry over and over again. People talk about peak phosphorus just like they do peak oil. There's only several places in the world that it can be mined. Florida is one of them, but there's only a 40-year supply of that. Morocco is another place, and there's about a 300-year supply. Phosphorus is not being recycled, and once that hard rock goes, there's a real question about whether or not we can survive. When phosphorus runs out, you aren't going to eat. Many of these building blocks that we use as chemists because thermodynamically and kinetically they go and they do the work that we ask it to do. The problem is, if we run out of it, how are we going to do what we need to do? If we don't become better at using it, we're not going to have the feedstocks. We're going to continue with poor process efficiencies. We'll have missing data. We're still working with high hazard materials in our processes. We have human environmental exposures. We've got a lot of legislation. There is a definition on sustainable chemistry, and it's really, the difference here is renewable resource conservation as opposed to efficiency, and that's an important one. Risk minimization, pollution prevention. Don't have a lot of time to go into that definition. Green chemistry historically has been two things that I mentioned before. One is the reduction and elimination of hazardous materials. The other is waste reduction. Two obvious things. The most important thing about green chemistry is source reduction. And that's rooted very firmly into pollution prevention, which was an idea that the EPA generated in the early 1980s. You prevent at source. Green chemistry takes it one step further and says we want to redesign molecules so that we don't create the problem to begin with. So I hope in the brief time we've had is that you see some of the presuppositions that drive much thinking around sustainable and green. Many people want to get caught up in defining things, which is a waste of time, and I'd ask you not to do that. Key elements. It's not that these things are going to disappear and we aren't going to get them. It's at what cost, economically, socially, and environmentally, to get these materials. Okay? We will, in all probability, invent ways of doing it, but it isn't going to be simple. And right now, it's really easy. Most chemists, when they say, where do things come from, what's the answer? If you say, where would I get, I don't know, a chemical from? They'll say, I get it from Sigma Aldrich or Fisher, right? They don't think about all the other places. So think about that, and I'm getting the hook to stop. So the last point I would leave with you is that implementation of these things will take time. And that's why it's so critical that all of you begin to think about this, internalize it, and make a difference in the future. So thanks very much. And we're going to go on into a reflection and discussion period now. So, in their packet, they should have the first exercise, right? So the intent here is for you to, at your tables, exercise 1 is to discuss these particular questions that are there.